Welcome.
What's up?
Hey, everyone. Today is a very interesting episode.
Mm-hmm.
We spoke on energy.
Yes, indeed.
Or what the Greeks called energia. Maybe it's more
Beautiful
G.
pronunciation.
Maybe it's
Juan.
more of a G, right? More of like a...
Oh, you might be right. Not sure.
Maybe,
I don't know Greek.
no,
Was it Latin or Greek?
He was Greek.
Okay. Anyway.
Either way, you know, if you were always wondering, like, what the hell is energy? We also were wondering, and so Terence here did a little bit of research, and, you know, we kind of just tackled the issue. What is energy?
Yeah, so we talked about the history of energy, basically. So you guys will, you know, actually hear how the whole thing developed. You know, we talk about Noether's theorem, which is one of the big, you know, mathematical generalizations. To give you energy conservation. And anything else, Juan, I miss?
No, but it's kind of I mean, we'll throw a couple terms out there that are a little kind of abstract and mathematical. But we do our best to try to define them as we go along, and so hopefully this can be applied generally. And if we didn't, well, you know, leave us a comment. Be like, you guys need to get
shit
better
on
at
us
this.
there.
Shit on us there, yeah.
But yeah, guys, just make sure you, you know, subscribe to our channel, like, share, comment again.
Yes, and go to the Twitter page because like Terence mentioned, that we have some interesting stuff that you can follow up on our Twitter page.
Yeah, got a video in there by, I forget the guy's name, it's Nick something.
Yeah.
But we're at Eigenbros on Twitter.
Yes.
And then, of course, on Instagram as well. All the good platforms, you know, you can find the audio anywhere pretty much.
Yeah.
Apple, Spotify, Google Play.
Yeah.
And yeah, guys, stay tuned.
3, 2, 1. We're live.
We live.
Hey, everyone. We're back on this special episode once more of Eigenbros. Thank you for listening.
Yes.
Yeah.
And what's this episode on today, Juan?
It's over energy.
Indeed.
It's you know, we're gonna try our best here after listening to some feedback here. I don't know if you want to take that for me.
Yeah.
To try to, you know, try to have a little bit of more formal kind of what would you say, like layout?
Yeah, I guess more of an outline to our podcast.
Scripted,
we had a couple of good criticisms from shout out to the IDW Reddit. That stands for Intellectual Dark Web. So I don't know if you're familiar with
Jesus.
I don't know if you're familiar with Eric Weinstein, Jordan Peterson.
I know Eric. I know of Peterson.
Yeah. Sam Harris. Ben Shapiro, all those guys are in the intellectual dark web. Okay. I'm not really a big fan of Ben Shapiro, though, but he's in there, apparently. Joe Rogan, I think, is in there.
I can't believe Joe Rogan's in there.
Well, I think he's not really. He's like kind of a loose member. I think he calls it the ineffectual dork web.
I mean, I would agree with him on that one. I would call it the dork web.
Yeah, but some of those guys are next level. Like Eric Weinstein, I'm a huge fan.
Yeah, Eric's cool. From what I've...
Yeah, he's fucking awesome.
He's a cool guy. I mean, just from listening to that one episode. Anytime any physicist that he has on, I'm like, okay, these are cool.
Well, I think
guys.
he's technically a mathematician. So,
yeah.
Tomato
at his level, I guess.
Yeah.
Right.
But yeah. Anyway, so on to energy. So
yes.
I guess I wanted to ask you first, Juan. What's your take on energy, man? What's some things that kind of come to your mind when you think of energy?
Energy.
Yeah.
Energy is God. No, I'm just kidding.
Wrong answers. It's God. Kind of is, though.
It kind of is.
Yeah.
If you think about the one sort of principle that you cannot, that you must abide, the law is like conservation of energy, and that's the one thing that we don't really understand why it exists, but it exists. It's just a property of nature that is there.
Right.
Yeah, I don't know if any physicists have tried to make sense of it in a deeper framework. Have you read anything on this?
Yeah, let's not jump the gun.
Okay,
but
I
can at least tell you a little preview about it. It's I think Emmy Noether probably did the best job of that.
Yeah.
So I know you're probably familiar with Noether. I'm probably not saying her name right, but
Noether.
I think it's like Noether or something.
We'll spell it out for you guys. Noether.
Bingo.
Yeah.
Look at Mr. Juan over here with the spelling cred.
Yeah.
But so for the non-physicists out there, Emmy Noether, I'm going to call her Noether. I don't remember how to say her name correctly, but she's a mathematician, probably one of the most influential people, besides like Einstein during his era. She's one of the big hitters that, kind of got her credit a little bit too late, because of course she was a woman back then. They didn't really have the best support for women in the sciences. And, even like, I think it was like Hilbert had to put his name on her lecture for them to even take her seriously at all or something. And they called her like the assistant professor or something.
Yeah.
But Emmy Noether, she created this theorem of mathematics that, as Juan was saying, the conservation of energy is one of these big concepts of physics. It's basically in the physics Bible.
Yeah.
And she kind of extrapolated that concept to a more generalized viewpoint.
And mathematically.
Yeah, we'll get more into it later as we go on.
So what would you say is like the formal definition?
Okay.
For energy.
So yeah, we actually got that. And Juan, I think you might have it on your computer. Or maybe I have it here. Let's see. Okay, yeah, we've got it here. So just reading from Wikipedia, it says, basically in physics, energy is the quantitative property that must be transferred to an object in order to perform work on or heat the object. So, that's kind of the definition that I had in my head of energy, I guess you could say. But, it's not really that satisfying. I mean, what do you think about that?
No, but that's because I think we try to derive more of an intuitive sense of energy. Like you don't really see, unless you're really paying attention, you really see like energy. You see this transference property of energy that, and you sort of, it's not immediately obvious to you that energy can't be created or destroyed.
Right,
is what I'm trying to say.
Right. It's not intuitive, right? It's not like this a priori, it's obvious to see this.
Yeah.
Yeah.
It's not, because like your everyday experience is, what would you say is an everyday experience that points to the opposite, like the counter of it?
Well, I don't know if there is.
Yeah.
To me, the concept of energy itself is already a non-intuitive kind of thing.
Yeah.
Which is the whole reason why I thought this podcast would be very useful to do, just because energy itself to me doesn't make sense. Or it's something that I don't think I ever would have thought of on my own.
Yeah.
But actually, it's kind of interesting because now that I've gone through the history of the energy, which is what we'll kind of talk about here today, the concept of energy actually seems much more attainable to me now. We kind of, in physics especially, I'm sure physicists, you guys can vouch for this. A lot of times when we're in our subjects, you kind of think of like, you kind of take these concepts for granted. And you're kind of like, wow, like, I don't know how these people came up with all this shit, but it must have taken some real geniuses to make all this stuff.
Yeah.
And it's so simplified and things are so well hashed out now. You can kind of get lost in how these things were developed.
Yes.
And actually,
because you get the impression that it's how did one person ever come up with this? But it's built on the shoulders of giants, as Newton said.
Exactly. So you kind of get a disjointed perception of this. You get a false perception of how these concepts were created.
Yeah, like the Greek term for energy.
Yeah,
right? That's energia. I'm using some Latin. I'm using Latin to pronounce that.
I think you might be close.
Yeah, probably. It's very close. Mediterranean Latin. It's all the same shit.
Yeah.
But yeah, even they had this concept of energy, and if we did our job right, we should have asked people what they think about energy in some form or manner.
Yeah. You're alluding to our potential video we could be doing.
Yeah.
We're going to do it.
We're going to do it.
Yeah.
Okay, so cool. And even they were thinking about it, and at up to what, 4th century BCE?
Yeah. So you see in the notes there, Juan, it says the Nicomachean Ethics.
What the hell is that?
So the concept of energy came first from Aristotle, actually, if you can believe that. So Nicomachean, and I looked up, was actually, it's either his son is named, I forget the actual name, but Nico is related to either his son's name or his father's name. So Aristotle called the Nicomachean ethics, he named it after his father or his son, and it's kind of a way of, it's like a philosophy of life, how the enlightened man should live. You know, I thought that was pretty interesting, and that's the first time they used the word energy.
So he came up with this woo kind of concept.
Yeah. Maybe it wasn't woo, I'm not necessarily sure, but the first instance it appeared. Yeah, I think it's nothing like the concept that the energy that Aristotle came up with was not related at all to the concept of energy now. Okay. The word was co-opted, much later. The word usage of energy came much later after the Nicomachean ethics in like the 1800s. And this is 4th century BC. So
yeah. I guess the official definition that we use today is closer to what is in the standard SI units of how we define energy today. Right now the definition of energy is more like is what is a joule, pretty much, right? Like the working definition, right?
Right. So of course, the physicists out there will know that the SI unit of energy is the joule, and it says, which is the energy transferred to an object by work, of moving at a distance 1 meter against a force of 1 Newton. So you can kind of visualize that, when you're looking at, imagine if you have a box just sitting on the ground. If you move that box 1 meter, against gravity, gravity is not 1 Newton, but we can just pretend it's 1 Newton for now. That would be, you're giving it energy now. So you've now given that box potential energy. And then once you drop that box, now you've done work. It's the exact opposite. You can think of work and energy as opposites. And then, of course, as we know, Juan, the work-energy relationship actually relates potential energy to work. So work is just a negative of potential energy. So if you don't understand that, don't get too caught up, guys. Just think of potential energy as like, it gives you, it's like this energy that shows you the ability to do work. So like a battery would be a way of having a store of potential energy. That's kind of the classic example. Yeah. Because, it's got all that energy stored up. Once you actually connect the circuit, now you've got, electrons flowing and you're doing some things. So that's the SI unit of energy is the joule. And that, of course, is thanks to the James Prescott Joule. His vapes are sick.
He died from vape sickness, the mysterious vaping sickness that's plaguing people today.
Right.
But yeah, like the most, how would I say this? I think I kind of iterated this already, but someone very important to physics, like a character like Feynman, he's probably one of the most eloquent physicists we've had. Yeah. Right?
Like a great explainer.
A great explainer, yeah. He's one of these people that are revered for understanding the concepts to a good enough level to explain them to a layman. Right. I think it's because, it's he's uniquely American. Yeah. He's probably the only physicist I can think of is that uniquely American with all the character traits of of most Americans.
That's true, huh? A lot of these physicists seem so unattainable because they're like, these cold Russian.
They're mostly international people. They're usually not U.S. native born people. It's but he's one of the people that you see that's like uniquely American, and he kind of gives his take in what energy is in the Feynman lectures. He says that he's kind of explaining conservation of energy to people, and this might, correct me if I'm wrong, but this might be one of the lectures that's on YouTube. He has a lecture series on YouTube.
He does, but this is actually
from his book.
If you're talking, so if you're referencing what's in the script here, what's in his book is the one that I've written here.
I see.
But he might have something similar on the lectures,
check
but I think
those out.
I think he talks more off the cuff on those, though. Although I know he has a script on his podium, I think he's still more free in his speech than.
Check those out if you haven't already. That's a really cool lecture series of him.
Yeah. So basically, this thing I have in the script here, one is I wanted you to look at it. It's just something that I wrote because I thought it was a good.
Yeah, he gives a good summary. He says conservation of energy states that there is a certain quantity, which we call energy, that doesn't change, doesn't change when nature sort of, how do you say,
undergoes her processes or something, I guess.
Yeah. So that is it's a really abstract idea because it's based on it's an axiom, right?
Yeah.
It's just like this. We can only say that this quantity is conserved, meaning at the initial state you have energy A, and at the final state you have energy A, and that's
right. Ideally.
Ideally. Yeah. Well, in conservative, we call this.
Exactly.
We call this conservative systems.
Yes.
Yeah. And all that means is that your system is it's a closed loop. The universe, some might say, is a whole closed environment. So, I think I don't know if this is up for debate, but but the total energy in the universe should be conserved.
I think it is up for debate as long as we don't know everything about the universe.
We don't. Yeah.
But it's accepted by scientists that everything is conserved in the universe.
Everything should be conserved.
Right. Even with black holes.
Yeah.
That was the whole conundrum with black holes, because at least they still have the black hole radiation, right?
Yeah, right. Meaning some of these big ideas, we can always go back to conservation of energy to help us answer them in some way.
Yeah.
But anyway, he just pretty much states that it's not really an intuitive thing, because like me and Terence were saying, it's not something you deal with in your daily life. So we kind of have to build analogies to describe what it is. So
right.
Yeah.
So, and there's actually another important point in there, Juan. So it says, if you see after, it says, not Einstein, Feynman also says, it says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. So that's pretty much it. So very interesting. It's like even Feynman doesn't really give a tangible thing about energy. It's kind of like this abstract idea where it's like,
well, this is what it does.
Yeah.
Like this is what we see.
It's a number that we calculate, basically.
Yeah.
He gives some more in the Feynman lectures. I thought there were some interesting things. He actually goes through an analogy about blocks. But it still has that, once he uses the blocks, he takes them away, and then it still becomes kind of an abstraction. But I was trying to think more if I can give even more explanation for what energy is. And, energy is so many things, right? Like mass is energy. We found that with Einstein.
Yeah.
There's a mass-energy relation, E = mc squared.
Yeah.
So your mass contains energy. If you converted your mass, let's say if you burnt your mass, for example, or maybe not your mass, that might hurt, but if you burnt some mass, a lot of times, our systems of power, a lot of times we still use steam.
Yeah.
If you're burning something, you're burning matter, it creates steam.
Yeah.
You can use that steam to do something. That's energy.
Yeah. Energy matter relation is something that's, to us today, it might be obvious now because we kind of have, like you were saying, batteries, right? They store energy, but those inside that battery is just a bunch of, it's just chemicals.
Yeah.
Like a certain arrangement of molecules in such a way where, you can make electrons sort of store energy.
Right. Right.
And yeah. But anyway, what you almost wanted to kind of bring up this thing called, Viz, what is it? Viz Viva? How do you pronounce that? Viz Viva?
So it's Viz Viva.
Yeah.
Or I guess it's Viz Viva.
Okay.
If you want to get really technical with the Latin.
What does that
That sounds
mean?
dumb though.
How does it relate to energy?
Yeah,
this whole
so
energy controversy.
this is kind of the meat of the discussion here. I wanted to go through the history of the viva. I'm going to call it the viva because that sounds fucking stupid.
Yeah.
The viva controversy.
Yeah.
So this is kind of the development of how energy was conceived. So viva, I've actually got a definition from Wikipedia here. So viva, I'm going to read it from Wiki. It says, from the Latin for living force, is a numerical term used, the first known description of what we now call kinetic energy, in an early formulation of the principle of conservation of energy. Okay.
Okay. Yeah, and as physicists will let you know, like, there's an essential distinction between types of energy, kinetic energy and like potential energy.
Right.
So that's kind of interesting that they had this. So, but what's the crux of this? So are they kind of the controversy behind all this is what exactly?
Okay, so when learning about the viva controversy, it was very interesting to me because there was this kind of weird crossover between science, theology, and philosophy that you really don't get.
Oh, so they
now.
So that's interesting. So they were at like a crossroads where they're like, "What the fuck is energy?"
Yeah, it was actually really interesting, man. Because like I was reading through the old papers of like Descartes and Newton, and Leibniz, and basically it's like they're talking like it's crazy because like some of their assumptions, let's say especially Descartes, like it's a metaphysical assumption. He uses things like because God. X, Y, and Z. He says one of the reasons for the conservation of energy concept was because he says because God in his perfection, makes things move like movement is conserved or something around along those lines. That's why you should have some number that is always conserved because God is perfect in his motions. He's the prime mover, so that movement must be conserved. And that's like a really interesting argument, right? It's like a metaphysical argument.
Yeah, they're operating in a theological framework.
Yeah,
for this.
Exactly. So it's a weird mixture that you just do not see anymore. So these guys are like, they're not only scientists. They're like trying to find. They're like in that weird spot where they're scientists, theologians, and philosophers at the same exact time.
Yeah.
So it just shows you like back in the days when things weren't understood, it's like. These heavy hitters, like they're a crossover between religion, science, and philosophy. Like all these things are kind of the same now. And all these things now have branched out now to their own things.
Right.
And of course, the most useful of them being sciences.
I mean, you know
how to take that shot, Juan. I'm sorry.
You do. I know. I wouldn't expect anything less.
Okay, so I got here.
So you're saying there's like a defining moment when Descartes said he defined momentum or something. Like,
are you looking at the script?
Yeah, he's trying to describe like this.
Yeah,
because they're talking about conservation of energy, and then they're talking about you're saying they were talking about movement now. So now there's a conservation of momentum in a way.
Well, that's the thing. This is the controversy. So the viva controversy in a nutshell. Gottfried Leibniz, we're familiar with him. He's the infamous Newton's rival.
Newton's rival in calculus. If you guys don't know about him, he's if you've taken calculus, he's has a distinct style.
Yeah.
In like writing out his calculus notation. As opposed to Newton. I think Newton used like letters like D over dx.
No, that's Leibniz.
No. Who's the one who used the primes?
That's Newton. I thought the dot notation was Newton.
Oh, okay.
Because remember, Newton's. Yes, this is the thing. This is important actually because Newton's system was inferior to Leibniz. This actually held back the English.
Oh, yes,
because they would not use. The Leibniz notation, which is superior, because he treated it like a coefficient, like a quotient in a sense. There's this funny thing, this kind of a meme where physicists will treat physicists say like dy over dx is a quotient, and the mathematicians will facepalm. But it's kind of like we use this is for the calculus people. This is the derivative. operator.
Yeah.
We treat it like a quotient. Don't mind if you don't understand what that means, but this is the Leibniz notation. This is the more powerful notation. Newton actually used a different notation, which held back sciences for them.
For right now, a derivative is basically the operation of taking the slope at a point.
Right, the instantaneous slope.
Yeah.
If you don't understand that, it doesn't matter. It's fine.
Yeah, you don't need it for this discussion. But that was okay. So you're saying this ties into this in some way?
It actually doesn't, which is kind of interesting. It's like when we all know about the Newton Leibniz.
Them duking it out.
The whole contention between them. Yeah. They actually are also having contentions in this fucking viva controversy.
So the rivalry is deeper than just calculus notation.
Man. So I was like, I didn't realize how deep they were of rivals. Although I guess it's a little bit looser because it's more Leibniz has kind of the rivalry mostly with Descartes, I guess you could say. But Newton kind of is more on the Descartes side.
Oh, okay. So Newton has a friend. He's an ally.
Yeah, but of course Descartes is dead by this point. This is another thing that we I think a lot of mathematicians and physicists don't get is we don't really have a time period or time frame of when these guys existed. Yeah. So Descartes preceded both Leibniz and Newton
by hundreds of years, probably, right?
I don't think that much. I think he just barely preceded them. Maybe he did. I forget. I think it's 1600s though. But I'd have to look it up.
Okay.
Early 1600s, and then Leibniz and them were late 1600s.
Maybe a generation or two.
Yeah, maybe a generation.
Yeah.
But, Descartes preceded them, and he formed his own version of, I think they call it the quantity of motion. But not to get ahead of myself, let me see. I just wanted to make sure I touched on the kind of the nutshell of vis viva. So let me go back. So it says,
nah, bro, you're good. You're building on it, man.
The two theories are now understood to be complementary, essentially. So the thing is, so that was actually an important point, though, because it's funny, like Newton and Descartes were actually kind of describing the conservation of momentum.
Yeah.
Leibniz actually was kind of describing the conservation of energy.
Oh.
At the time, they didn't know.
They couldn't make the distinction.
Yes. So the vis viva controversy, as I said in the beginning, was more related to the kinetic energy.
Yeah, because I mean, what you said when you said Rene, or Descartes said that God preserves like translations or movements or something like that. That made me think, oh, he's talking about momentum.
Right. Exactly.
Because I mean, now I'm operating obviously in this framework where I already make that distinction.
Yeah.
But him using that language, I'm like, oh, he's talking about momentum. He's not talking about energy.
Right. And actually, Juan, there's this next part of the script that I have you on here, right?
Yeah,
but it's really long, so I don't know if I want you to read all that.
No. I mean, we can kind of touch upon those points, like just saying, like, how Descartes was defining momentum as, he was defining momentum as mass and the speed of an object.
Right.
Defines its momentum.
And that's very important that you said speed.
Yeah.
So Descartes actually even was distinct from Newton in the sense that Newton actually was more for mv, and v is a vector. So it's momentum times velocity in a sense. And Descartes was momentum times speed.
So speed, for the record, velocity is speed with a direction.
Yeah. So for those of you who've taken introductory physics, velocity is distinct from speed because it has magnitude and direction. Speed only has magnitude.
Yeah, it's just a number.
Yeah. So with Descartes, he was very, what would you say, like very surface level in the definition because he only took into account the speed.
Yeah.
So he didn't even take into account like if you had two balls that bounce back with each other and they had different directions of momentum, but they'd still be conserved. So he only looked at magnitudes.
Yeah. Interesting.
And then Newton was kind of an evolution of that because he looked at the actual velocities and it's like the vector form now.
Yeah.
So it's got negative sign for velocity if you're going backwards and a positive sign is going forward.
Yeah. So
continuing on.
Yeah. I mean, so in his framework, in this Cartesian momentum definition, momentum isn't conserved in a way, right? Because you don't have vectors opposing
Descartes.
Yeah.
Right. Well, it is conserved in a rudimentary way, right? So it's like it's conserved if the system's acting in like if both the speeds are like in the same direction or something.
Oh, I see.
Yeah, so it's like a more surface level form.
It breaks down in more rigorous terms when you add on direction.
Right.
Yeah.
Like, and a lot of these things, man, if you read these papers, they're so unlike any of the papers that we read today. It's really interesting. I suggest anybody looking into this, like maybe we'll even put the links up on the YouTube. You should go back and look at these old papers because they use like no math. They're talking about all these concepts. They treat this like a philosophy paper. They do use diagrams and things, and it's like all this crazy geometry. They love geometry, but the mathematics is not really there. So a lot of these things are being ascribed to their talks after the fact. Like, I don't think Newton or Descartes were saying mv or absolute value v for speed. You know, they're all talking in a way where it's a very philosophical approach.
Yeah, and I mean, by that time, like, what's his name? Huygens?
Yeah.
Huygens established that, like, you know, the sum of an object's mass times the speed, like basically times the speed or whatever v squared. Is conserved in collisions in which the objects pretty much bounce off each other.
Yeah.
Right. So by that time, they already had that idea of like, what is it called? It's sort of a conservation of momentum for elastic collisions.
Well, it's an mv squared.
Yeah.
So it's the conservation of energy.
Okay, so they're saying. Oh right, yeah. You're right. Yeah.
So this is after the fact, after Leibniz, because actually I don't know if we explained this, because Leibniz, you know, Newton is mv, right? So he's talking about momentum. Leibniz is talking about mv squared as well. So Huygens, I think, establishes this later on.
Oh, so Huygens comes through and is like, oh, this is energy v squared. Adding mass times velocity squared gives you, obviously, well, if you look at the units,
speed squared, I think.
Yeah.
Which is the same.
Yeah. If you look at the units, right?
Yeah.
It comes out as energy.
Yeah.
I
don't know if he claimed it was energy yet, but this is one of the controversies. Which one is the vis viva, or the life force? So you can already tell they don't know what it means.
They're not like, using dimensional analysis.
They don't even have names for these different concepts.
Yeah.
They don't know. They think that there's some godly conserved quantity or the life force.
Yeah.
But they don't know what it is. They don't know if it's mv or mv squared. So then, let's see, continuing on, Juan, where are we?
Yeah. But like how this ties into Newton's second law, or Huygens had already kind of like tried to define like Newton's second law. And and this guy, what's his name? Wallace? Who's this Wallace guy? Where does he come
I believe Wallace might be an engineer.
Okay, so he's just like,
but I'm not sure. Don't quote me. I can't really tell you much about him because I didn't.
But he comes out of nowhere. He comes out of nowhere and gives an accurate description of what would you say the
conservation momentum. So these guys are all after the fact. This is kind of just showing what the history is after.
Okay, so
this whole thing.
They're building up on it.
So they actually are giving these things some solidification to the concepts. And that's good enough. So the Cartesian thing is the quantity of motion is what Descartes called it. So just remember that term in case we use it again.
Yeah.
But this is the vis viva controversy of the life force, and they're kind of debating which one is the life force. So Newton, Leibniz, Descartes all have these concepts that are like they don't know which one is the life force. Okay, so it says basically the main problem is Leibniz and Descartes were talking about two different concepts, as we said. So it's momentum and kinetic energy. So the most important issue between them is basically it's boiled down to language. So they just don't have the language for the two concepts. And and this basically spawned Descartes' philosophy was written in his Principia Philosophiae, or Philosophiae, however you say it.
Yeah, but then Noether comes around, right? So after all is said and done, maybe.
Well, this is a little bit jump the gun, maybe. As I put in there, Noether, but Noether, she didn't come till way later.
Yeah, she doesn't
because she's during Einstein's era.
Yeah, like late 1800s.
Yeah.
Yeah.
So
at least 200 years later, probably.
Yeah. So I guess we can. So pretty much the script.
No,
is,
150
is,
years later.
The script is finished there, but we can continue on. So
yeah,
let me see if I can wrap this up kind of nicely in a way that makes sense. So, we have Leibniz and Newton basically having a contention between momentum and conservation of kinetic energy.
Mm-hmm.
The thing is, what we know is Leibniz was pretty much accurate in a lot of his statements, because he noticed that the reason why Leibniz didn't like the living force being, or the vis viva being mv, is because he actually saw that momentum is not conserved when you drop a ball from point A to point B. So as you know, when you try to calculate mv at the top and the bottom, if you drop the ball, it's not equal, right?
No.
So that was his problem. You get a change in momentum, actually. And that's because the gravitational force is acting on it. So it's actually not conserved.
Mm-hmm.
So I don't know if they were that sophisticated enough to know that, but he noticed that when you're dropping a ball in the air or something, the momentum is not conserved.
Mm-hmm.
But he did notice that mv squared was conserved, which is why he was like, oh, this is the real living force, right?
Yeah.
And he also noticed that it worked in elastic collisions. But then, of course, people found the flaw in his argument, which was, you notice that kinetic energy, we know, physicists know, kinetic energy is not conserved in any elastic collisions.
Mm-hmm.
Right? So when you calculate a collision that's inelastic, you notice that the energy is not the same for an inelastic collision. The kinetic energy is not the same for an inelastic collision.
Mm-hmm.
So then the momentum people are like, no, this is the living force. Because mv is always conserved with inelastic and elastic collisions. So this is where the contention happened. So they're like, we don't know whose living force is the best.
Yeah. Interesting.
It fails in certain regimes. Kinetic energy fails when you're trying to conserve inelastic collisions. Momentum, mv, fails when you're trying to conserve force, or when you're trying to conserve energy, or when you're trying to conserve the momentum in a force field, let's say, when there's an external force acting on the system. So this is why they both had so much time to argue.
That's funny, because we also kind of have arguments like that today, because we go, let's say, we work in different frameworks for certain problems.
Mm-hmm.
And the frameworks that we operate in, we go back and forth between the energy framework and the momentum framework. Isn't that interesting? Depending on the problem.
Right.
So it's not...
And a lot of times we use both. We just love to have as many...
Flexibility.
Yeah,
of
energy
choice.
and momentum conservation are like so great to have, because it's like we almost get two free equations for free, you know, a lot of times.
Yeah.
You know, and that's what you need to be able to solve physics problems, you know.
Yeah.
A lot of times, because you'll have like two unknown variables, and that's such a great thing that we take for granted a lot of times.
Yeah, it's so true. Like, it just seems so interesting that these guys were duking it out and didn't know that, you know, that
they're giving...
Why not both?
Yeah,
the
exactly.
Whole situation, you know?
Right.
Yeah.
So I guess...
But, yeah, so anyway, so that's like a nice little bow on it, I think.
Yeah, so I guess we can talk about Noether a little bit.
Yeah, when she came around, so...
Yeah, so Noether, you know, she came around way later. She's Einstein era. 1800s and things around there. 1900. I think. Maybe not 1900.
Yeah, early 1900s, yeah.
Yeah, I can't remember. But, yeah, Noether is really interesting because she kind of made it so that she put a bow on, like, everything, pretty much, here, because... She showed that, let me see, is there a definition?
Yeah, you give the definition.
Yeah, so I have the definition here. So it says that energy, that every differentiable symmetry of the action of a physical system has a corresponding conservation law. Now that statement is actually very rife with a lot of high-level concepts.
Yeah.
So if you don't understand what that means, I get it. Most importantly, the biggest words in there are going to be symmetry and action, I think. We kind of talked about what conservation laws are. You know, it's just something that gets conserved. And differentiable might be one, too, if you don't know calculus. But it's just basically saying that there is some property. What? You pointed the camera.
Yeah. That's because the battery on that one is.
Oh, is the battery messed up?
Yeah. Well, I'll give you a second. I'll explain what it says here.
Yeah, pull that in. Plug that in.
But yeah, all Noether's theorem says is that a symmetry of a physical system can be described as how would I say this? Let me see. Basically, the physics. How would you? Okay, I'm just gonna wait for Terence.
Yeah.
Wait for this. Okay.
So this one's kind of hard to explain, but
to the layman, yes, because we deal with this in physics quite a bit because we've developed whole formalisms behind this theorem.
Yeah.
You know, we talk about the Hamiltonian framework, the Lagrangian framework to solve problems. I mean, these are all both different forms of things. So Hamiltonian is the energy framework.
Yeah.
And then the Lagrangian framework.
Hamiltonian just basically means total energy.
Total energy framework. And then the Lagrangian framework, which is the difference.
Yeah, the difference between energies.
Yeah.
So difference between kinetic and potential energy.
Yeah, and this one is interesting because the Lagrangian framework is typically used, I think, to prove Noether's theorem because what her theorem says is that your physical system will take a path of least action, meaning the minimizes the energy overall.
Mm-hmm.
Right? So
I don't know if that's her theorem.
But that's kind of...
I think that's actually Lagrange might have invented the principle of least action.
No, you probably...
Not sure, though.
But I think she generalizes it, if I remember correctly.
Okay.
And yeah, so in that framework, though, you have these ideas of action and minimizing action.
Yeah.
And
action is like, I don't know what the fuck that really means still.
Well, if we want to give you some idea, it really, that to me is the living force. Because it's energy moving in time. I wouldn't say the argument me and Terence have gotten into before is you would want action to be defined as energy per unit of time.
Okay, yeah.
But you're saying that's more intuitive.
Yeah.
But
that's just because I hate times. I hate anything that's something times something because I don't know what that means.
Energy
really.
it's coupled with time in this action definition. But the more intuitive definition would be if it's energy per time.
Yeah, but let's anyway, not even go down that rabbit hole.
Let's not go.
Me and Juan have already had like 2-hour discussions about this, about action. Action's one of these hard concepts that even like I as a physicist still don't really understand.
It's interesting. It's interesting. I think it needs to be discussed more in classes, but it's kind of not. So yeah. Anyway, to give you to go back to the definition we're giving here, a symmetry of a physical system is a feature of the system that you're dealing with. It's either observed, it's obvious to you, or it can be intrinsic.
Well, I actually have the definition of symmetry too that you might have pulled up one. You can read maybe the Wikipedia on that. Because symmetry is not like what you think. It's not like this thing has two sides, therefore it's symmetric. It's actually like a specific kind of symmetry.
Yeah.
Meaning like translational symmetry.
Yeah. Well, that's what she's arguing.
Rotational.
Right? Yeah, but she's arguing
some people
that,
might not understand that symmetry doesn't mean that it's like the shape
looking
of
at a
the
mirror
object or
something.
Yeah, exactly.
Yeah,
it's different. It's like a mathematical symmetry that has to do with like translation, rotation, things like that. Time symmetry. Yeah,
so symmetry in physics is how would you say so you put the definition in here actually.
Oh, did I?
Yeah. So it's something that's preserved or remains unchanged under some transformation.
Okay, cool.
So yeah, like Terence was saying, you by transformations we mean that you can move in space.
Yeah. Rotate it.
Mm-hmm. It looks the same.
Right.
You can flip it over an imaginary axis and it still looks the same. And she basically observed this property, like, oh, you can change the system in any sort of way,
right? And
it will look the same still,
right? And the conservation of energy actually pops out of Noether's theorem if you take the derivative of the Lagrangian with respect to time. So if you take the derivative, the Lagrangian again for the non-physicist is if you subtract kinetic, or if you subtract potential energy from kinetic energy.
Mm-hmm.
So just know it's like, instead of adding the two energies, kinetic plus potential, it's the opposite.
It's a difference in energy.
Yeah, it's taking the kinetic minus the potential. So
Yeah.
you're getting a smaller number. So you're usually looking for the smallest number with action and things like that. But that's the Lagrangian. So if you take the derivative of the Lagrangian with respect to time, it's actually a nice proof too. You'll actually get out the Hamiltonian if you arrange it correctly. And that Hamiltonian is equal to the total energy.
Yeah.
So it shows you that energy is conserved when there is no time, when there's no dependency, no explicit dependency on time.
Mm-hmm.
You can have an implicit dependency on time, which just means like velocity can be a function of time, but your Lagrangian cannot depend explicitly on time.
Yeah. It's
Sorry if that's too high level for some people, but it's very hard to explain this in any other simple way.
No, I think it's.
I'd have to take a really long time to try to do it.
Nah, I think it's pretty sufficient.
I can't do it well enough. It's okay.
Yeah.
I think I could do better if I actually had more time, but I can't right now.
No, I think that's a pretty sufficient like definition, because all she's saying is that you can move. For example, you can move. You can try this. You can move a ball.
Mm-hmm.
You can throw. What's the best way to? What's a good example of this? You could say. Let me make an example. So let's say I throw a ball to Terence, and in that motion, let's say it has some energy that I transferred whatever energy into the ball or whatever.
Okay.
Right? If I were to somehow live in an upside down world,
Mm-hmm.
the physics of that wouldn't change, right? Assuming everything is equal, assuming everything is the same. And if I were to,
it's better if you think of it as not on Earth. It's easier if you think of it like in space, because we know everything in space.
Okay, yeah,
doesn't change. The thing is, when you have gravity in there, it fucks everything up.
Okay, all right. Let's put ourselves in space.
Yeah, if you throw in space, like you cannot differentiate if you're upside down in space or right side up.
Yeah.
Unless you have some point of reference like the Earth or something.
Yeah. So there you go. Put yourself in space, and then the physics shouldn't change.
I've actually got a little video on Twitter from I forget the guy's name, Nick something. If you find it on Twitter, it says something like Noether's theorem explained simply. I've got like a 1-minute video on there from another YouTuber.
Check it out.
on there.
Go to the Eigenbros Twitter page,
and he does a nice explanation that's very quick of explaining the power of Noether's theorem or why it's useful. Yeah.
So there you go. I mean, we use this theorem so that we can make generalizations about a problem like. Well, we say canonical transformations, meaning the physics is preserved even though we switch coordinate systems a lot of the time. And like you can do these kind of things, like you can translate your system or you can move it in some way to make it simpler for you to solve using internal symmetries of the problem.
Right.
So
symmetries are king in anything mathematical and physics.
Yeah, because it makes it easier for you to solve or
it can reduce the complexity of a problem down if the system you choose is such that it takes advantage of the symmetries involved in the problem.
100%.
Yeah. And conservation of energy is like one of these things that's just like it's just so useful to use because that's already like such a powerful thing, and if you can make that even simpler with symmetry, then you're fucking gold.
So she basically gave us that theorem that helps us sort of at least justify to ourselves that what is legal.
Yeah.
And what we
it's like a generalized way to always know if your energy is conserved. Her theorem also proves if momentum is conserved as well, and then also if angular momentum is conserved. So you get like all these things from her theorem in a generalized framework where you can always see, is my system, like you don't have to think, you just say, is my energy conserved in the system? I don't know. I'll do the operation and see it. And yes, it is.
It's so powerful.
Yeah. So these things, when you of course, the higher levels you go with math and physics, you get these great theorems that make it so, you think that when you get smarter, you actually like your brain gets bigger. It's actually like it's smaller because you don't have to think about anything after a certain point. It's like when you get so high up, you have so many tools at your disposal that are made in such a way where they generalize things so much sometimes that you actually have to think less because you can just exploit these rules that you know that are always pervasive in the universe.
Yeah.
And you see, these symmetries are present. No, I'll just rotely do this now.
Yeah.
Because it's easy to see this now.
Yeah. Spoken like a true physics professor,
right?
It's so easy to see the symmetries.
Well, I won't be so out of touch to expect freshmen to do it, but I wasn't doing calculus at kindergarten, as some professors seem to think.
Some professors, no. Some professors seem to think calculus is a preschool kind of affair or something. I don't freaking know.
Or it's the classic, people always tell the Gauss story about how when he was 3 years old, he solve this problem. His age just gets lower and lower as it goes on.
No, I had this professor who said his cat could do calculus. And I was like, dude, just shitting on students. It's like, we get it, you're smart.
Calculus is great though. I think calculus is probably the most useful math to learn.
Really, it really is.
If you want to get such a bang for your buck, learn calculus.
Yeah, because it's an analytical treasure trove. In terms of you can do so much with this. It's so powerful. Yeah, its usefulness.
You just get so much out of it.
Yeah.
For such a low price.
I mean, really, you only need a year, maybe.
Yeah.
To learn
Calculus 1, I think you just you can cook. You're cooking it with a lot of stuff with Calc 1.
If you spend time learning calculus in 1 year, you're going to be so better off.
Yeah. So if anybody's on the fence about learning some math, you would try. You're like, should I learn calculus? Definitely worth it. You could just look at some lectures. You just learn about the derivative, learn about the integral, and learn about limits, and that's all you need.
And the integral is just the antiderivative.
Yeah, exactly.
So it really just comes down to the derivative.
Yeah.
So,
but anyway, back to energy. Juan, did you have any thoughts, any questions? You had some interesting questions that you may have had about energy.
Energy.
Do you think you learned anything about the history, or what? Any comments?
It's just a nice little bow on it, I guess. And energy,
Do you feel less stupid that you know how long it took these guys to figure this out?
Yeah, because it gives some framework as to. These guys, it's a new concept. It's something that we're all building on, and it's kind of amazing to me that some people, we take it for granted a lot of the time that these concepts weren't exactly fleshed out from the start so easily.
Right.
We build complexity onto it and refine ideas into a digestible form that we have today. And and I guess it kind of makes it more interesting. Do we have definitions of things that are wrong? Maybe.
Right.
Because it's
we'll fix.
Yeah, maybe there are things that we
sure.
That's because I mean, we're having discussions about debates about quantum mechanics and stuff. And that
we've definitely got some things, right? For instance, the cosmological constant. We still have debates about how fast the universe is actually accelerating and things, or expanding, I guess I could say.
Yeah.
So there's definitely some things that need to be resolved, right? We don't even know. I don't want to get into that,
but it made me appreciate the whole thing about energy, the Leibniz debate about energy, and then Newton debating about momentum. What's a better framework to work in?
Right.
And
them calling it the life force. I thought that was just cool. It feels to me, it feels more understandable now. It doesn't feel so disconnected. I feel if I existed at this time, I could see myself going through this path actually.
Yeah.
Whereas before I knew this history, I was I don't think I would ever in a million years come up with the concept of energy. I don't even see how that would happen.
Well, you have an interesting addition to this, I think. Because you were the one who told me the form of kinetic energy wasn't even really formulated until recent.
Yeah, kind of late.
Yeah.
I think Coriolis was the guy who added in the 1/2.
Really?
Yeah. So everybody was using MV squared. And then I think Coriolis was the guy to finally be guys, it's 1/2, and then this is equal to potential. And then they're oh, shit.
Well, because it's always nice, because kinetic energy always has the form 1/2 mv squared.
Right.
So when you take the derivative, you get the momentum.
Right.
but it wasn't immediately obvious.
No.
To some people that
these scrubs out here were all using MV squared.
Yeah, because what the fuck? You get a 2? You get a 2 when you take the derivative. What did that come from?
They just shrug it off.
That's twice the momentum. What the fuck happened?
But you know what's crazy actually with this too, man? With the energy, the whole development of energy. I've even got a nice little PDF that has the entire development of energy. I don't know if it's going to be important for now. You may not.
We can
be able
give
to
the
use
title out actually, but it's called a mathematical overview of mass and energy conservation in modern physics.
Yeah, but there's even another one. I've more something else on there that gives the entire history. But one thing I've said, I noticed was it was actually the development of thermodynamics is when they got all these concepts on lock. And it was the engineers that actually solidified all this.
Oh,
so when there was actually a vested interest in producing
steam engines,
you know, all the modern industrial revolution, all this kind of stuff, that's what actually prompted them to really solidify these concepts and actually find out the relationship of how heat was energy. Because a lot of times people were saying like, we're losing energy, but like we don't know how this makes any sense. And then they realized only later, like, oh, when they were doing all the steam engine stuff and all this stuff, it actually was heat was actually a form of energy. And when they added heat into the equation, then they were actually getting a balance of the equations. So a lot of this development this is hundreds of years of development of the concept of energy.
Yeah.
And it, you know, they're really the guys who stamped the bow on it were all the engineers. Like William Rankine, I think, and then some of the other guys. I don't remember their names.
Yeah.
But yeah, it's funny because the engineers and thermodynamic people are the ones who actually really solidified all those things.
Yeah. Huh. Yeah, this kind of reminds me of what if I don't know if this exists anymore, but Brian Cox had a series that I saw a long time ago, but that discusses exactly this. He talks about energy. And yeah, they talk about some of the engineering in the Industrial Revolution was leading the charge in all this physics.
Yeah.
Because the work-energy relation and stuff, and then like how heat.
Yes, exactly, the work-energy relation.
Yeah, and I mean, physics, necessarily there was a lot of overlap between engineers and physicists at the time.
Yeah, maybe so.
Because, I mean, but I think physicists had to be
also
hired.
need to swallow their pride now a little bit because engineers basically invented thermodynamics.
Well, they had to be hired in a way because, like, industrialists had to figure out what they're like. We need to minimize the cost of certain things. Like, for instance, like shipping things from across the country. They needed to get ice blocks from Antarctica or something, just to ship produce from one state to another. So they needed to figure out how to, one, insulate things properly, how to, and basically how to reduce, like, basically heat isolation, all this other stuff that you need to know your physics.
Right.
Of how heat works.
And it wasn't developed well enough.
And it wasn't developed enough,
yeah.
So they had to hire physicists to figure it out. And yeah, those guys came through, and then they had to engineer those things, and yeah. It was an
crazy.
It was an iterative process that led to kind of our smoothness, our sort of understanding today. So
yeah, it's kind of funny. I didn't even realize that thermodynamics was going to tie into this, and I actually was watching some cheesy little film on Netflix.
Yeah,
it was called Las Leyes de la Termodinámica.
Okay,
and
so
it was
Spanish.
Yeah, so it was about some dude trying to tie in thermodynamics with love.
Oh God.
It was kind of interesting because it was so confusing. It's like no movie I've ever seen.
Okay.
Because it looked like a physics documentary.
Yeah.
Superimposed onto a love story. It was very strange, man. Like if anybody wants to check it out on Netflix, check it out. I think it means just the laws of thermodynamics, but it's in Spanish, and it's really interesting. You should maybe check it out with your girl or something sometime.
I might check it out.
It's kind of interesting. You're gonna be like, what is this movie? It's very interesting.
Maybe he's trying to argue that his love is like a law.
It was. He was basically trying to put the physics of thermodynamics, and I think even more than thermodynamics, onto his love situation.
Okay.
Like it's interesting. You can see it. Like for instance, he was dating this really hot supermodel, and he would call her like a black hole type person because she's so dynamic and has so much like she doesn't have mass, but she pulls people towards her.
Okay.
And like he would be
She's
like a nebula or something.
You're sucking all my light.
Yeah.
You're sucking the life out of me.
Yeah. Well, that's kind of like what it was.
Oh,
and,
okay.
And then he would put like quantum mechanics in there and things, and they'd put a bunch of real physics into the movie. That's
interesting.
And it's like, it was like good because I was watching it with a girl too, and I was like, this movie really is boring as fuck. But then I was like, it's kind of helping me because it's not boring, but it's I don't ever watch love movies on my own time.
You're like, it's kind of corny and stuff. You're like, I wouldn't watch this if it wasn't for
but the physics like saved
subtext.
it, because I was actually able to, get something from it. So I was like, okay, I like how he's trying to relate physics to this love story.
That's nice. Maybe I'll check it out.
Yeah.
It seems just, that's funny though.
Yeah. I'm curious to see what you would think.
Yeah. Next week we'll give a thorough review of this.
No, we can't waste the podcast on that.
No, you're right. But yeah, I think. What about you? Did you have any other insights? Oh,
you
said
final thoughts or something?
Yeah. Any final thoughts?
Not really. I mean, I just always wanted to get a better. I'm glad I did this podcast because I just wanted a better understanding of what the hell energy was.
Yeah.
When I was. Even before now, I was still like trying to think of what the fuck is energy. Like, how did it look, like, what images even come to my mind? And I get like Dragon Ball Z, spirit bombs, and
chi and
and Transformers Energon and shit.
Yeah.
So I'm like,
didn't somebody on the comment section give a shit about that too? Because we were like the vibes or something. Something about we get bad vibes from what's his name, Jeremy Corbell or something.
Oh, yeah. We made a comment about Jeremy's energy in the Commander Fravor podcast, and there was some person who's saying like we're not being rigorous. We're not being rigorous or something. Yeah,
but it's like okay, but you know what I mean, where it's like synonymous with.
But I think that was kind of one of those people you probably can't really talk to them because if they can't see our logic from the podcast itself, then you probably can't explain much to them. So I kind of just left it after that.
Yeah, we'll see. It'll be interesting to see. Maybe we can do a follow up, kind of short, quick follow up on what people say, what they think energy is. Yeah, we should leave a comment or question for people in the comments.
Yeah. So guys, actually, I think we're gonna end it soon. So what interesting questions or insights about energy do you think we missed? Do you guys have anything interesting about energy that you know, or maybe that you'd like to know even? Leave it in the comments.
Mm-hmm. Yeah. Please do. Or maybe even what you think energy is.
Sure. Yeah.
Like, is it something, did you think, is it immediately obvious to you, like what these people were arguing, or is it something that you're like, wow, I mean, it's just kind of like a thing. Maybe you just took it for granted.
Mm-hmm.
So, yeah, please comment on that. And,
Yeah. Cool, guys.
All right. Cool.
See ya.
Thank you for surviving.
Thank you, guys.
For making it this long into another episode of Eigenbros.
Yeah. Tell us if you like the script.
Tell us if you like the script idea. I know we're trying to work on it. We're trying to make we're trying not to be too scatterbrained,
we scattered as fuck.
We are scattered as shit. And so, it's because we're both, if you use Myers-Briggs, we're both, what is that called? Perceivers and extroverted intuition or something.
Yeah.
So we kind of just go everywhere.
Yeah.
We just kind of go everywhere, right? So
let us know.
So let us know if you like that. If not, if you like more off-the-cuff kind of stuff, like us just kind of bullet point stuff and, jumping around. Let us know, but yeah, it's also what we said in the last part, right? Leave a comment to let us know what you think about what you walked away with, and if that makes any sense to you.
Yeah.
Or if you appreciate it, at least that somebody's finally able to like lay this out in this particular manner, because this is not something that is even available to a lot of STEM students, like in a formal manner, unless you take a history of science class. Probably they'll even skip over this.
Right.
There's no like how these big concepts even came to be.
Right.
We felt it as a duty to ourselves. So
Indeed. So, guys, thanks for sticking around, and make sure to subscribe, like, comment, share, and check out our Twitter at Eigenbros. Go to the website, eigenbros.com.
Yeah.
We're on Instagram. We have the audio podcast on Apple, Spotify, Google Play, etc., etc. And we'll see you next time, guys. Thanks a lot.
Yes, peace.